Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his masters in structural engineering from the same. He is a doctorate from Anna University and he has also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIR on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series in bioarchitecture. Now we have a look on design of structures 2, lecture 5. In the previous lecture, we have seen we have worked out some example to find out the moment of resistance of a singly reinforced section, and also using the moment of resistance equations, we have designed the size of section as well as the area of reinforcement required for it. Now we move on to doubly reinforced rectangular section. What do you mean by doubly reinforced rectangular section? The section which is reinforced with the reinforcement or which is provided with the reinforcement both at top as well as at the bottom, that is both at the compression as well as tension zone, is called as doubly reinforced rectangular section. Under what circumstances the doubly reinforced rectangular sections are designed? Certain circumstances, due to structural or architectural recommendations, the size of sections can be reduced. Due to this, the amount of concrete area which above the neutral axis is completely reduced. In order to compensate this stresses or in order to supplement the stress in the concrete above the neutral axis, we are in the place of providing the reinforcement at the compression zone. When you provide the reinforcement at the compression zone, the section will become doubly reinforced rectangular section. Due to the reinforcement of the doubly reinforced rectangular section, the moment of resistance can be increased without altering the dimensions of the section, and this is the doubly reinforced rectangular section. So, due to structural or architectural considerations, the section will have insufficient area of concrete to provide for compressive stresses when you reduce the size of concrete. So, steel is placed at the part of compression zone in order to supplement the concrete in resisting the compressive stresses. So, when you provide the reinforcement at the top, that is at the compression zone, the section will become doubly reinforced rectangular section. So, here the moment of resistance can be again increased without altering the dimensions of the section. But what about the moment of resistance of the doubly reinforced section? The moment of resistance of the doubly reinforced section is the moment of resistance of the singly reinforced section plus the moment of resistance due to the compression reinforcement at the topmost extreme fiber. So, here also we are having 3 types of sections. One is balanced section, under reinforced section and over reinforced section, as in the case of the singly reinforced rectangular section. So, we have already seen what do you mean by the balanced sections. The reinforced sections are designed based on the assumption that the stresses in concrete and steels reaches their maximum permissible stresses one and the same time. Both the materials are stressed to their fullest allowable stresses at the same time. That big section is called as balanced section. In the case of under reinforced section, if you use less steel than that required for the balanced section, the section will become under reinforced. In such conditions, the steel is stressed to its maximum permissible value while the concrete is stressed below the permissible stress. Under such conditions, the section will fail initially due to over stress in steel. So, the type of failure which occurs in the case of under reinforced section is tension failure or ductile failure. And in the case of under reinforced section, the depth of neutral axis which is normally going to be, that is this neutral axis is normally going to be situated at the center of gravity of the section. In this section, this neutral axis which is moves upwards. When you compare the actual depth of neutral axis of the under reinforced sections with the balanced sections, here we got x is less than xc when the neutral axis moves, actual neutral axis which is moves upwards. When you come to the over reinforced sections, when more steel than that required for the over balance section is used, the section will be called as the over reinforced section. In such conditions, the concrete is stressed to its maximum permissible value, while the steel is stressed below its permissible value. Under such condition, the section will fail initially due to overstress in concrete. So, here the neutral axis moves downwards. So, here x is greater than xc, we get over reinforced section. Now, we move on to how to find out the moment of resistance of the doubly reinforced rectangular section. Now, how to analyze this section, how to find out the moment of resistance. So, as in the case of singly reinforced sections, here also we are going to find out, we are going to analyze and the doubly reinforced section, and we are going to find out the moment of resistance, which can be used for finding the moment carrying capacity of the respective sections. Once you find out xc, then you find out the x for the respective section. When you compare x with xc, we can finalize what is, whether it is an under reinforced section or over reinforced section or balanced section. Then we are going to find out the moment carrying capacity of the respective section. Then again, using these two moment of resistance equations, we are going to design the section, that we are going to find out the size of section, and we are going to find out what is the area of steel required for resisting those moment of resistance at the bottom as well as at the top, that is total AST required for the beam as well as the total AST, that is the total ASC, which is required to resist the compressive stress at the top. Now, how to find out the moment of resistance? Here, a doubly reinforced rectangular section. So, here this is the, since it is a doubly reinforced section, the steel must be provided both top as well as at the bottom. This is total AST required for the section, and this is the area of compression reinforcement, which is denoted by ASC, which is placed at D dash from the topmost extreme fiber, and B is the breadth of beam and small d is the effective depth of beam. This is a doubly reinforced rectangular section. Again, I am taking this as the neutral axis of the given section. And this one is the strain diagram. That is, maximum strain at the topmost extreme fiber is epsilon c, and this is epsilon t, the tension reinforcement. This is a strain diagram. And this is a stress diagram. So, maximum stress at the topmost extreme fiber is sigma CBC, and the stress at the distance d dash from the is called as sigma CBC dash, and T is the tensile stress, tensile force, and the equivalent stress diagram here it is this one. This is the equivalent stress diagram by transferring the area of steel into the equivalent area of steel. So, sigma CBC is the stress at the topmost extreme fiber, sigma ST by M is the stress in concrete surrounding tensile steel. This is we have already derived. Now, here this is, you take this as sigma CBC dash, which is at a distance d dash from the topmost extreme fiber. Now, to find out XC, you take this as XC and this is D minus XC. You take this as the equivalent stress diagram for balanced section. So, XC by sigma CBC is equal to, at a depth of XC from the neutral axis, the maximum stress is sigma CBC. At a depth of D minus XC from the neutral axis, the stress in the concrete surrounding tensile steel is sigma ST by M. This is the expression which is used to find out critical depth of neutral axis. Then to find out X, actual depth of neutral axis, To find out axial, normally here in the case of working stress method, while you find out the axial depth of neutral axis for the unbalanced section, we assume the neutral axis is going to be situated at the center of gravity of this section. To find out the depth of neutral axis, we are going to equate, that is by equating moment of area of compression side to the moment of area of tension side, or equivalent moment of concrete area of tension side. So, moment of area of compression side, which is equal to total area, that is B into X, is the area. Moment of area is, I have already explained you, moment of area equal to area into distance of CG of area from the neutral axis. This is the moment of area. So, distance of CG of this total concrete from the neutral axis, here it is x by 2. You take, this is the equivalent stress diagram of unbalanced section. Okay, you take this as x. Okay, now B into x by 2 plus or minus. Since the steel is placed at the compression zone, we need to first deduct the moment of area due to the compression steel. When here we have considered whole concrete area, first we need to deduct the moment of area due to the compression steel. Moment of area is area of the steel ASC into distance of CG of the steel from the neutral axis, that is x minus d dash, x minus d dash. Then we add equivalent concrete area on the compressive steel, that is m into ASC into x minus d dash. This is the equivalent concrete area, this is the area of compression steel, total concrete area. Then we deduct the moment of area of the compressive steel, then we provide equivalent concrete area of the compressive steel. So, the moment of area on compression side is equal to the equivalent moment of area of concrete on tension side, which is equal to the moment of area due to whole concrete above the neutral axis minus moment of area due to compression steel. Then I add moment of equivalent concrete area of the compression steel, that is m into ASC is the equivalent concrete area, x minus d dash is the distance of CG of the steel from the neutral axis. As per code, as per IS 456, where the compressive resistance of the compression in bars, where the compressive resistance of the concrete is taken into account, shall be the calculated stress multiplied by 1.5 times the modular ratio. So, sigma SC is equal to 1.5 times the calculated stress at the compression zone. So, if it is multiplied by 1.5 times with the modular ratio along with the stress, this area should also be again multiplied by 1.5 times. So, B x square by 2 minus ASC into x minus d dash plus 1.5 m into ASC into x minus d dash. This is the moment of area of whole concrete above the neutral axis. Then I have deducted moment of area due to the compression steel. Then I have add equivalent concrete area of the compression steel. So, here compression in bars, where the compressive resistance of the concrete is taken into account, shall be the calculated stress multiplied by 1.5 times the modular ratio. Here the stress is multiplied by 1.5 times the modular ratio, then this area should also be multiplied by 1.5. So, here which is equal to equivalent moment of concrete area of the tension steel. So, here C1 be the total compressive force which is offered by the whole concrete area above the neutral axis, which is normally acting at x by 3 from the topmost extreme fiber, and T1 be the corresponding tensile force and the distance between these two forces called as the lever arm Z1, and this is d minus x by 3. And here again C2 be the another compressive force which is offered by the compression steel, which is placed at d dash from the topmost extreme fiber, and to balance the force there is another tensile force D2, and the distance between T2 and C2 is again it is called as a lever arm Z2, that is d minus d dash. So, here this is the moment of area of the compression side, then which must be equal to equivalent moment of concrete area of the tension side, that is equal to m into AST into d minus x, where m is the modular ratio, A is the area of steel. When it is multiplied, AST is multiplied by the modular ratio, it becomes equivalent concrete area surrounding tensile steel, and d minus x is the distance of CG of the tensile steel from the neutral axis. So, here b x square by 2 plus 1.5 m minus 1 into ASC into x minus d dash, which is equal to m into AST into d minus x. This is the expression which is used to find out x for the doubly reinforced section. So, we have found xc and x. Now, we are going to find out the moment of resistance, the moment of resistance of the beam. So, now we are going to compare. If x is less than xc, it is under reinforced section. So, the moment of resistance Mr is equal to T into Z. This is we know that, and in the case of under reinforced sections, steel is stressed to its maximum permissible value first, while then the concrete is stressed below the maximum permissible value, the section which is normally fail initially due to overstress in steel. So, the moment of resistance is T into Z, which is equal to T1 into Z1 plus T2 into Z2, where T1 is AST1 into sigma ST into the respective lever arm Z1 d minus x by 3 plus AST2 into sigma ST into d minus d dash. So, the moment of resistance is moment of resistance of a singly reinforced section plus additional moment of resistance due to the compression steel. If x is greater than xc, it is over reinforced section. The moment of resistance for over reinforced section is Mr equal to C into Z, that again which is C1 into Z1 plus C2 into Z2. C1 here it is B into X into sigma CBC by 2 into d minus x by 3. This is the moment of resistance of the singly reinforced section plus the moment of resistance due to C2, that is area of compression steel, that is C2 here it is area of steel into, that is area of steel here it is equivalent area of concrete surrounding tensile steel is 1.5 m minus 1 into ASC into the sigma CBC dash into d minus d dash. This is the area, this is the corresponding stress at the level of compressive steel, this is the lever arm for the compression steel. Bx sigma CBC by 2 into d minus x by 3, 1.5 m minus 1 into ASC into sigma CBC dash into d minus d dash. This is the one we have derived. In this we have started analyzing the doubly reinforced rectangular section. In this also we have three sections, one is balanced section, under reinforced section and over reinforced section. This is the rectangular section which is reinforced both the tension as well as compression zone. The area of reinforcement of the tension zone is AST, area of reinforcement of the compression zone is ASC. So, here AST which is normally AST1 plus AST2 AST1 is which is used to resist the total compressive force offered by the whole concrete area, and AST2 is the additional reinforcement to compensate the area of compression steel. So, in this case we need to find out AST1, AST2 and ASC. So, total AST is AST1 plus AST2, total AST is AST1 plus AST. So, here this is the strain diagram, maximum strain at the topmost extreme fiber epsilon c, here it is epsilon t, and this is the stress diagram, maximum stress at the topmost extreme fiber is sigma CBC, and the stress at the level of compressive steel is sigma CBC dash. This is the equivalent stress diagram by converting the area of steel into the equivalent area of concrete, that is sigma CBC is the maximum stress at the topmost extreme fiber. At the place of concrete surrounding tensile steel is sigma ST by m, and sigma CBC dash is the stress at the level of compressive steel, that is sigma CBC dash, and here C1 be the total compressive force which is offered by the whole concrete area above the neutral axis, C2 be the total compressive force offered by the compression reinforcement which is acting at D dash from the topmost extreme fiber, T1 is the tensile force which is used to balance C1, T2 be the total tensile force which is used to balance C2, and the resultant distance between C1 and T1 is lever arm Z1, that is d minus x by 3, where C1 is the total compressive offered by the whole concrete area above the neutral axis which is acting at x by 3 from the topmost extreme fiber, and the distance between C2 and T2 which is the another lever arm, that is d minus d dash, where d2 is the tensile force which is used to compensate C2, where C2 is the compressive force which is due to the area of compression steel which is acting at D dash from the topmost extreme fiber. So, this is the stress strain diagram. From the stress strain diagram we have found the value of XC by equating from the similar triangle property of the balance section, we have found XC by sigma CBC equal to d minus XC by sigma ST by m. This is the equation which is used to find out XC. Then to find out x, in the case of an unbalanced section, since the neutral axis is situated at the center of gravity of the section, in order to find out x, we are going to equate the moment of area and compression side to the moment of equivalent moment of concrete area of the tension side. So, here B x square is the total concrete area above the neutral axis into the distance. So, that is area of the whole concrete in the distance of CG of area from the neutral axis. So, since the steel is placed at the compression zone, I am deducting that is the moment of area of the compression steel, area of the compression steel into distance of CG of the compression steel from the neutral axis, and I am adding the equivalent concrete area of the compression steel, that is m into AS into x minus d dash. So, the compression in bars as per IS 456, where the compressive resistance of the concrete is taken into account, shall be the calculated stress multiplied by 1 times the modular ratio. So, here the stress has been multiplied by 1.5 times with the modular ratio, this area should also be multiplied by 1.5. After simplifying this one, B x square by 2 plus 1.5 m minus 1 into AS into x minus d dash, which must be equal to m into AST into d minus x. So, this is the expression for finding out axial depth of neutral axis, and using this we have come to conclude that if x is less than xc, it is under reinforced section. So, the moment of resistance normally T into Z, where T1 into Z1 plus T2 into Z2. AST1 into sigma ST into d minus x by 3 is the moment of resistance of balance or a singly reinforced section. AST2 into sigma ST into d minus d dash is the moment of resistance to balance the compression reinforcement due to the additional tensile reinforcement. If x is greater than xc, we conclude that it is over reinforced section. So, MR is equal to C into Z, where C1 into Z1 plus C2 into Z2, this is the moment of resistance due to the whole concrete area above the neutral axis, and this is the moment of resistance due to the compression steel. So, using this we can easily design this, we can easily find out the moment of resistance. Now, let us have a look on the summary of this lecture. So, we have analyzed the doubly reinforced rectangular section by working stress design method. In this case, we have found the XC, that is the critical depth of neutral axis, then we have found the actual depth of neutral axis of the section. By using and by comparing this section, we have finalized whether our section is under reinforced or over reinforced, and based on the conclusions we have found the moment of resistance of the respective section, that is under reinforced and over reinforced and balanced section. And questions in this lecture Under what circumstances the doubly reinforced sections are designed, that is we have discussed detailedly. Second one, determine the moment of resistance of the doubly reinforced rectangular section. And references for this lecture is IS 456 2000 plain and reinforced concrete code of practice. This is the IS codal provision. Then a book, a detailed book that is written by S. N. Sinha on reinforced concrete design. With this we come to the end of this lecture. Thank you.